Everyone, we are learning about geometric sequences and series today. And so as opposed to the arithmetic sequences and series that we just did, a sequence is geometric when the ratio of successive terms is constant. Okay, so whereas with arithmetic sequences, we were subtracting to find a common difference, this time it's a ratio, so we're going to be dividing. And what we mean by this is I should be able to take any term and divide that number by the term that came right before it. And I should get the same thing every time. And whatever you get when you divide is going to be called the common ratio. So the way that we can define this recursively is a sub n equals r times a sub n minus 1, where a sub n is any number, any term. A sub n minus 1 is the number that came right before it. Okay? And the way that I can define my common ratio is like I just said, any number divided by the number that came right before it. Okay, that's a sub n minus 1. Okay, now the way that I can define this iteratively is a sub n equals a sub 1 times r to the n minus 1 power. And your common ratio cannot be 0 because that would be stupid, because then you would just get a whole bunch of zeros, right? If you take any number and multiply by 0, you just keep getting 0. So, I mean, that'd be pretty dumb. And then it gets a weird case where you like start dividing by zeros and it gets weird. So we're not going to deal with that. It's just a sub n times r to the n minus 1. Where we're defining r to be the common ratio. Where r is the common ratio. All right, so first example, I'm asking, is the sequence 2, 6, 18, 54, 162, ... geometric? So what I have to do is, well, let's just see. So I should be able to take any number, like 6, and divide it by the number that came right before it. In this case, I get 2. And I should be able to take a number like 18, divide the number right before it, and get the same thing. I should be able to take 54 divided by 18. Hopefully I get 3, which I do. And if I take 162 and divide it by 54, I should get the same thing again, which I do every time. So this is implying that if I take a number, divide it by the number that came right before it, I get 3 every time, which does mean that this is geometric, which means that my common ratio is 3, my first term is 2. Okay, remember, it's just always good to know what your first term is because that tells you more information about the sequence. Okay, next question. Is this sequence geometric? So this time I'm giving you a sequence, and it'll get to the point where you'll be able to look at it and tell, but for now, we'll go through a process. So I'm going to find my first term. So 3 times 4 to the first power, which is 12. So all I did was I plugged in 1 for n because that's going to be my first term. Okay, and just like we did on the previous example with arithmetic sequences, I'm going to find my second term as well, just to get an idea of what to expect from my common ratio. So in this case, I would get 48, which means that I'm expecting a common ratio of 48 divided by 12, which is 4. Okay, so let's see if that's true. So in order for that to be true, I need to find my common ratio, sorry, not my common ratio, my nth term. So my nth term is given, it's 3 times 4 to the n. And I need to find my n minus 1th term, or the term right before it, which would be 3 times 4 to the n minus 1 power. Okay, and then using the formula I gave you above, I should be able to find my common ratio by dividing any number by the number that preceded it, or the number that came right before it. Okay, well, if I'm dividing, 3 divided by 3 cancels out. I have two numbers with the same base, so I have to use my exponent rules now. And remember, if you're dividing two numbers by the same base, that means you can subtract their exponents. Which means I have 4 to the n minus n plus 1, which is just going to be 4. N minus n is 0. And 4 to the first power is just 4. So I get a common ratio of 4, which matches what I was expecting. So this is going to be geometric. If I take any number and divide it by the previous number, I should get 4. So my first term is 12. My common ratio is 4, and that's what I was asking you to find. Okay, let's move on. So I'm given a sequence, kind of ugly, and I'm asking you to find the nth term of this sequence. Well, in order to find the nth term, I need a couple things. I need my first term, and I need my common ratio. Okay, well, in order to find my first term, I just look at it, it's 10. In order to find my common ratio, I just need to divide any number by the number right before it. The easiest one to do would be 9 divided by 10. Hey, now if you divided 729 over 100 by 81 over 10, you would also get 9/10. You would get the same thing. You can try it yourself if you don't believe me. Okay, so to write out the nth term, I'm just going to go all the way back to my to the equation that I gave you in the box up above. So it's the first term times r to the n minus 1 power. So it's my first term, which is 10, times 9/10 to the n minus 1 power. And I'll put this in parentheses. Okay, moving on, finding the ninth term of the sequence. Well, I'm just going to plug in 9 in for n. So I have 10 times 9/10 to the 9 minus 1 power, which is the same thing as 10 times 9/10 to the 8th power, which if you plug into your calculator, you get about 4.304, which is fine. That's going to be the ninth term. Okay, and then moving on, I need a recursive formula. So my recursive formula is going to be whatever my common ratio is times my previous term. So in this case, my common ratio is 9/10. I'm multiplying by my previous term. And remember, for recursive formulas, it's especially important you have to give at least one term. So my first term is 10. Okay, that makes it possible for me to find my second term and so forth. Without that, I couldn't. Okay, so let's talk about finding the sum of a geometric sequence, and we're going to use this a lot next year when we get to sequences and series, but for now, we'll just go over some vocabulary. So the term finite just implies that my sequence or my series will have a beginning and an end. Okay, so if you have a sequence that doesn't have an end, meaning it goes on forever, it's not finite, it's infinite. And if you have a sequence that somehow has an end, but it doesn't have a beginning, so like on a graph, it would go forever to the left, then that means that that it is also infinite. So it's not going to be finite. Finite just means like a line segment, it has a beginning, and it has an end, and it doesn't go on any more than that, as opposed to a line with arrows implying that it goes on in both directions for forever. Okay, now convergent just implies that my series or my sequence will approach a number. Or in other words, it means that the problem has a solution. Where, as opposed to that, divergent implies that my sequence or series increases or decreases without bound. So what I mean by that is it increases in size or scope or whatever we want to call it. It increases for forever. It never stops increasing. Okay, so I'll show you a quick example of this. So like on a graph, if we graph the function e to the x. Okay, now if we approach this graph to the right, so as we go right along this graph, I see that my graph gets really, really big and it keeps getting bigger. And if you know anything about e to the x, exponential growth, it just implies that as my x value gets big, my y value is also going to get really, really, really big. It does not converge to a number, it diverges, it goes towards infinity. Okay, now on the other hand, if I go to the left, so as I follow this line to the left, something we know about e to the x is that it gets really, really close to 0, but it doesn't never touch 0. And that's what convergent really means. Okay, I'm approaching 0. It doesn't necessarily mean that I'll ever touch 0, but I'm approaching 0. And so I would say that e to the x sort of converges to 0 to the left, whereas to the right, it goes on to infinity. Okay, and we'll go through some examples of this. But a couple more just definitional things. So we will be dealing with infinite geometric series. An infinite geometric series converges if and only if my common ratio is less than 1. And I should say the absolute value of my common ratio, meaning that my common ratio is between -1 and 1. If it equals 1, no good. If it's bigger than 1, definitely no good. If it's smaller than -1, definitely no good. The absolute value of my common ratio has to be less than 1. Okay, now the sum of a geometric sequence can be represented as a series. So we'll go back to series notation or sigma notation. And so this is what it would look like. A lot of times starting from 1 to n, and we can talk about indices or changing your index later. But the inside looks just the same as our iterative definition of a geometric sequence. It's just inside of a summation notation. And now what this means is that I'm taking a whole bunch of numbers and adding them together. So my first term plus my second term, which I find by multiplying by r, and then my third term, which I find by multiplying by r again, plus so on and so forth until I get to my last term, which I've multiplied by r n minus 1 times. Okay, and this is a lot of numbers. It's not infinite, but this can be a lot of numbers. It totally depends on where my index stops, whatever this top number is. And it can be a lot. So a really, just an easier way of calculating the sum of one of these series here is the formula a sub 1 times 1 minus r to the n divided by 1 minus r. Right, so this is just a shortcut. If you are given a finite geometric series, and notice that this is finite, meaning there's an end, you can take the information in your sum, plug it into this formula here, and it will give you an answer. Okay, as opposed to down here, notice up here I have an infinity. This is infinite. Okay, this series is going on for forever. And so it's the same thing as this, except it never stops. Okay, it just keeps going and going and going for forever. And the way that we would find the answer to this is by very important formula, a sub 1 divided by 1 minus r, where a sub 1 is my first term and r is my common ratio. Okay, this is really important. We're going to use this again next year, so may as well get used to it now. All right, let's go through an example. We'll do an example of an infinite series first, and then we'll do some more in class if you have questions. But first, I just want to go through a quick proof showing that 0.999 repeating is the same as 1. Okay, well, 0.99 repeating is the same thing as 0.9 plus 0.09, right? Plus 0.009. So each time I'm just adding an extra 0, and I'm adding a 9. So I'm accounting for every decimal in my infinite repeating decimal. And I'm going to keep doing that. Okay, well, in fraction form, 0.9 is the same thing as 9/10. 0.09 is the same thing as 9/100. That's 100. This is the same thing as 9/1000, and so on. Okay, well, this is a series. Let's take a look at it. I see that with the pattern continues that my denominator will keep increasing with another 0 at the end, which means that I'm multiplying by a 10th every time. I'm multiplying the difference between this term and this term is a ratio of 1/10. So if I multiply my first term by 1/10, I get here. If I multiply this by 1/10, I get here, and so on and so forth. So I see a couple things. My first term is 9/10. My common ratio is 1/10. And again, you can, even if you didn't see that, you could find your common ratio by taking any number dividing by the previous term. So if you divide 9/100ths by 9/10ths, you would get 1/10. Okay, well, I can set up a series from this. This is an infinite series, and if I just use the formula that I was given at the very beginning, I know that I have my first term times my common ratio to the k minus 1 power. In this case, we're using k. You could use n. It really doesn't matter. Okay, well, in order to find the sum of an infinite geometric series, you're going to use the formula a sub 1 over 1 minus r. Well, a sub 1 is 9/10 in this case. That's my first term. R is 1/10, which you can hopefully see where this is going. 1 minus 1/10 is 9/10. I have something divided by itself, which is 1. So there you go. It's just a relatively easy way of showing that 0.9 repeating is the same number as 1. Now, we didn't actually prove this, but hopefully you just take my word for it, for now at least. Okay, so that's it for this video. I will see y'all later.